Hello friends, so today I will talk about some common continuous distributions. This is a note that I have uploaded a week ago. I hope you have at least looked at the notes. So first of all, let us understand what do we mean by a continuous random variable. So a random variable is continuous if probability x equal to y is 0. That is, if you are assigning 0 probability to point sets. Okay, now if the underlying sample space is finite, that cannot happen, because when the underlying sample space is finite, then if we assign 0 probability to each and every outcome, then the sum of those probabilities will be equal to 0, which will violate the second axiom, which is that probability of S is equal to 1. But I had told you that the continuous probability distributions refer to situations where the underlying probability space is uncountable. Then we have seen examples where the underlying probability space is uncountable, but the probability assigned to each outcome is 0. That does not violate the second axiom, that is P of S is equal to 1, because then probability of this set is not equal to the sum of the probabilities of the elements of this set. Why not? Because then the third axiom holds only for countable collection, but this is an uncountable collection. So that's it. So basically, one thing you should bear in mind whenever we talking about continuous distributions or continuous random variables, the underlying state space cannot be finite. In fact, it cannot be even countable. It has to be uncountable. So continuous probability distributions or continuous probability models refer to situations where this underlying sample space is uncountable. Anyway, let's not worry about it. This is something I have told you just to make your concepts clear. But the definition, you can say simply probability x equal to y is 0, 0 for all real number y. Now obviously x cannot be this cannot be true for any simple random variables for the same reason that I have mentioned. So x must be a random variable that takes uncountably many values. Only then this can be true. So if you say that x is a random variable that takes countably many value with probability 1, then this can never be true. So this is the definition of continuous random variable, but this implicitly means that the range of this function is an uncountable set. Anyway, the equivalent definition is that probability x less than equal to y is equal to probability x less than y. Why is that so? Because if you see difference of first of all, see that this event, that probability x less than equal to y, is a superset of the event x less than y, because it has one extra element that is those points in the sample space for which xw is exactly equal to y. So that is not here. So this probability cannot be less than this. Remember, if A is a superset of B, then probability of A cannot be less than probability of B. So the difference is always going to be non-negative. Their difference is exactly equal to this probability x equal to y. So the condition x equal to y is 0 is equivalent to that probability x less than equal to y is same as probability x less than y. Now this part is slightly technical. I don't know whether you can see that or not. Anyway, so in general, when you look at probability x strictly less than y, that is not exactly the distribution function, rather the left limit of the distribution function at y. Anyway, this point we will revisit when we will talk about properties of distribution function in detail. The distribution function is always right continuous. This is also a property. We have not proved it. Therefore, the above condition implies that a random variable is continuous, that is probability x equal to y is 0 for all y. Okay, this should be happening for all y. Okay, so this for all is also important. If it happens for only 1 or 2 y, then that's not what is a continuous random variable. So if this is happening for all y, then this is same as saying that the distribution function is a continuous function. Why? Because this is a right continuous function, and under this condition this function is pointwise equal to its left limit. So therefore it's a continuous function. So we can say that a random variable is continuous. So I'll add one line here now. So x is continuous if fx CTRL plus is a continuous function on the real line. The probability distribution, so this is what it is. Now what do we mean by a continuous probability distribution? Well, it refers to the distribution of a continuous random variable, or it refers to a probability function that assigns zero probability to point sets. So now there are some more terms related to continuous distribution. So a non-negative valued function little f is said to be the probability density function PDF if this distribution function you obtain by integrating this non-negative valued function. So by fundamental theorem, then what will be the derivative? So then what will be the derivative? So of this fx, this derivative of fx will be equal to fy, or f is the antiderivative of f. So does is this true for every distribution function? Of course not. For example, Bernoulli distribution binomial for discrete distributions, there is no density function. But for continuous distributions, you can have a density function, that is, you can find out a non-negative valued function f such that integrating that you compute probabilities. And you see that if you define the distribution function like this, then this is a continuous function, right? Because this follows from the properties of integral. So if you look at the properties of antiderivatives and from the fundamental theorem, this is clear, right? Because this is a differentiable function, so it has to be continuous. Now then we can define something called the kth order moment like this. This is y to the power k fy dy. Now this will be the kth order moment provided this integral exists. Now for odd powers of k, this may not even exist for all distributions. We will see such examples, and now we will define the moment generating function as this integral. So instead of y to the power k, only change will be e to the power ty, because we have a note on MGF, right? You remember what was MGF? It was expectation of e to the power tx. So it will be e to the power ty fy dy. Now again, this makes sense provided this integral is finite for all values of t in some neighborhood of 0. Now when you have a moment generating function, then we call that distribution light tail, and when we don't have a moment generating function, we call a distribution heavy tail. Now if a distribution has moment generating function, then obviously it will have all the moments. But if a distribution has only finitely many moments, that is, suppose these integrals exist for k equal to 1, 2, 3, or after finitely many values they don't exist or are not finite, then that obviously distribution cannot have MGF, and then we'll call them a heavy tail distribution. So here I am saying that you can why are we defining all this? Because if you want to specify or identify or write the definition of some continuous distribution, you can do either by specifying the formula of the distribution function, or the density function, or moment generating function. At different times different things are convenient, but they are all equivalent ways of identifying a probability distribution uniquely. So first distribution that we will look at is the uniform distribution. It is also called rectangular distribution. So here I am writing down both its distribution function and density function. So distribution function, as you can see, is what will be the plot of this function? Simply it is 0 to the left of 0, and it is the straight line joining 0 0 and 1 1. A 45-degree straight line 0 0 1 1, and beyond 1 it is 1. So you can imagine this curve. Now obviously you get this function by integrating this function, which is 1 on the interval 0 to 1 and 0 elsewhere. Now you see here, if I have strictly less than, you could also write down less than equal to, it doesn't matter, because you know Riemann integral value does not depend on the value of the function at one point. So it is integral 0 to 1. So whether it is closed interval or open interval doesn't matter. Now the MGF of the uniform distribution I am asking you to verify. So use this formula to compute the MGF. So although I am in general writing integral over the whole real line, but in practice you see it will be on the support of this function f, right? Support means what? The closed set on which this is positive, and in this case it will be the interval 0 to 1. So the MGF will be actually integral 0 to 1 e to the power ty fy dy. So you compute that integral and it comes out to be this e to the power t minus 1 by t. Now this will be, this is a finite quantity as long as t is not equal to 0. For any value of t, it is a positive quantity. Why? Because for positive value of t, e to the power t is greater than 1, so this difference is greater than, so this difference is positive divided by t, and when t is negative, so the numerator is negative, so is the denominator. And this I am leaving as an exercise. This I want you to do is that find out the kth order moment of this distribution. One point I would like to tell you, whenever you look at a distribution where the density function is vanishing outside some interval, outside some interval of finite length, there all the moments will exist and the moment generating function will also exist, and that will be a light tail distribution. In fact, we say that distribution has no tails. So understood what I am saying? That whenever I have a distribution where whatever be the formula of the density function PDF, if it is vanishing outside some interval, here it is vanishing outside 0 1, so for some distribution it may be vanishing outside set 0 to 100 or 10 to 100. Whenever you see that it is vanishing outside some interval, then you know that for that MGF is a finite quantity for all values of t, and and then the moments will exist for all k, and so on and so forth. Now one question, what will we know that mx of 0 is equal to 1, but this function is not defined at 0. So why is it that so? Because you take the limit t tends to 0, that will be exactly equal to 1, right? L'Hospital's rule. Now next is the exponential distribution. So this is so here you see, when we say that x is following uniform distribution, so what is happening here? The probability why it is on 0 1, because you see the density function is vanishing outside the interval 0 1. So it means that there is no probability assigned to values outside the interval 0 1. So here what is the range of x? Range of x is from 0 to 1. So x is taking non-negative proper fractions as its values. Now exponential distribution, here also I have written out the distribution function and the density function. Now you can see here that the density function is the exponential function e to the power minus y, and integrating that we get the distribution function. So it is vanishing only for negative values of y, and for all positive values this density is a positive quantity. So for this distribution the random variable is non-negative valued. It can take values greater than 1 with positive probability. So